In this session, we are going to talk about the basics of a new topic, which is trigonometry. If I were to split this particular word, trigono means something related to triangles, and metry is nothing but measurement. That is, this particular topic is going to talk about some measurements that are related to triangles. The field of trigonometry is applicable for all types of triangles. However, till 10th standard, the study of trigonometry is restricted only to right angled triangles. That means in 9th and 10th standard, we will apply trigonometry to only those triangles which are right angled. So right angled triangle is basically a triangle which contains a right angle. This particular field, the field of trigonometry, is used in our day-to-day lives for purposes like measurements of heights, measurements of distances, navigation. In the field of navigation also a lot of trigonometry is used. Even applications like Google Maps might be using a little bit of trigonometry. So the field of trigonometry is definitely useful in schemes of wherever you are measuring distances, or you are measuring heights, or where navigation is involved, like in case of pilots or in case of creating maps, a lot of trigonometry can be used. Sailors in the sea definitely use trigonometry to calculate the distances between, say, their own ship and the other ship, or their own ship and the other two ships, and so on, or the distance between them and the coast. So trigonometry has a wide range of applications in many fields. So in today's session, I am going to introduce trigonometry to right angle triangles. But please keep in mind that trigonometry can actually be used for all types of triangles. Like trigonometry can be used in acute angle triangles or in obtuse angle triangles. But for the time being, for your 9th and 10th standard, we will be dealing with trigonometry that is restricted to only right angle triangles. So let's consider a right angle triangle. Let me explain the concept now. Let's consider that there are two right angle triangles. So let's assume that I have a right angle triangle, and then I've created one more triangle over here, right? So consider that you have triangle ABC, in which angle B is a right angle, and you have drawn another line which is DE, a line segment DE, where D lies on AC and E lies on BC, and DE is also perpendicular to BC. You will notice that there are two triangles over here. So let us note down some important points. There are two triangles that I see in this particular picture. Two triangles in the picture. Which are these triangles? I have triangle DEC and I have triangle ABC. Right? These are the two triangles. In both the triangles, the angle C is the same. Angle C is held constant. Right? Angle C is held constant. That means whether you measure angle C in triangle ABC or you measure angle C in triangle DEC, the measurement of angle C in both cases is exactly the same. Okay. Now, assume that the EC is of length 4 centimeters. Let's take some lengths. Assume EC is of length 4 centimeters and assume that DE is of length 3 centimeters. Now, using Pythagoras, I definitely know how to find the value of DE. I can say by Pythagoras Theorem, I know that DC is the hypotenuse, so I can say DC square is equal to DE square plus EC square, and therefore DC square can be given as 3 square plus 4 square. That means DC square is equal to 9 plus 16 which means DC square is equal to 25, or I can say that DC is 5 centimeters. That means this length DC is 5 centimeters. Now let us do one thing. Let's assume that the length BE is 4 centimeters. What it means is this complete length is say 8 centimeters. Okay. So can you make a quick guess as to what will happen to the length AB? Let me repeat this. We have a right angle triangle DEC where EC is 4 centimeters. Okay. The length EC was 4 centimeters. Now I have doubled the base. The base was 4 centimeters. I have doubled the base to make it 8 centimeters. That means BC is 8 centimeters now. Can you guess what will happen to the measure of AB? I will give you a few seconds to think about this before moving on. So my intuition tells me that because the base has been doubled, the height should also get doubled, right? This is just an intuition that I have, correct? So this particular height should now become 6 centimeters. The height of the original triangle was 3 centimeters. So this 3, because the base doubled, I can say that by my intuition, I feel that the height should also be doubled. That is, the height should become 6 centimeters now. Now, is it possible to calculate the length of AC? Of course, yes. I can again use Pythagoras Theorem. So I can say in triangle ABC, I have AC square is equal to AB square plus BC square. AB square is 6 square and BC square is 8 square. So that's going to be 36 plus 64, which is 100. And therefore I can say that AC is square root of 100, which is 10 centimeters. That means this hypotenuse is now 10 centimeters. If you take a look at all this very closely, you will notice that the sides have changed. So EC was 4 centimeter, BC became 8 centimeter. Similarly, DE was 3 centimeters, AB became 6 centimeters. DC was 5 centimeters, AC became 10 centimeters. But there is some pattern over here. Do you notice that all the sides have actually doubled? Meaning, the 4 centimeter side became 8 centimeter, the 3 centimeter side became 6 centimeter, and the 5 centimeter side became 10 centimeters, right? So I agree that the sides have changed, but if you notice very carefully, they have changed in the same proportion. So let's make a nice table out of this. So if I make this table over here, the original base was 4, the original height was 3, and that's why the hypotenuse was 5. All in centimeters. In case of the enlarged triangle, that is triangle ABC, I have my base is 8 centimeters, my height is 6 centimeters, and the hypotenuse therefore became 10 centimeters. You will notice that all this happened because angle C was being held constant. So if your angle C changed, then you wouldn't get the ratios in or all the sides wouldn't scale by the same factor. The very fact that we have maintained angle C as constant, that is the reason why you are getting a perfect enlargement of these triangles. So what I can now say is the sides of triangles have changed. the sides of the triangles definitely have changed, no doubt. The sides have become bigger, but the question that comes to my mind is the ratio of these sides also changing? That is the question that I wish to answer now. So what I'm going to do is I'm going to pause for a few seconds. I'm going to allow you to take a look at this particular section before I start finding the ratios of different sides. So consider these two triangles that were there in the earlier case. I have drawn them separately over here. Angle C is same in both the cases. So let us label these angles as equal angles, right? These two angles are exactly the same. Now if I want to label some sides with respect to this angle C, which is the opposite side? The opposite side is DE, right? The side that is opposite to angle C is DE. The side which is adjacent to DE, to angle C, the side which is adjacent to C, adjacent means neighboring or besides. So don't consider DC as the adjacent side because that is always the hypotenuse. Don't consider hypotenuse as either the opposite or the adjacent side. So hypotenuse will remain DC. So the adjacent side to angle C is EC, right? In this particular figure, in triangle ABC, the opposite side to angle C. So with respect to angle C, the opposite side is AB. With respect to angle C, the adjacent side is BC. Adjacent side is BC. And the hypotenuse happens to be AC. Right? So now what I'm going to do is, in both the triangles, I'm going to find the few ratios. So let me find the ratio of opposite side to the hypotenuse. So the ratio of the opposite side to hypotenuse, opposite side is 3 centimeters. The hypotenuse is 5 centimeters. Centimeter cancels, therefore the ratio is 3/5. In this case, the ratio of opposite side to the hypotenuse is going to be, with respect to angle C, the opposite side is 6 centimeters divided by the hypotenuse is 10 centimeters. Centimeter cancels, 6/10 becomes 3/5. You will notice that both the ratios are exactly equal to each other. So this is a very important conclusion. What it is telling us is, as long as you maintain the angle constant, as long as angle C was being maintained constant, the sides will change, no doubt about it. So the sides of the two triangles are very much different from each other. However, the ratio of the sides will remain the same. So let's note that conclusion over here. So as long as the angle remains the same, the ratio of opposite side to the hypotenuse is the same. So in both cases, the ratio was 3:5. Similarly, I am now going to find the ratio of the adjacent side to the hypotenuse. So for example, in this case, with respect to angle C, the adjacent side is 4 centimeters. divided by the hypotenuse is 5 centimeters. Centimeter cancels, so the ratio is therefore 4:5. Whereas in case of the larger triangle or the enlarged triangle, let us find the ratio of adjacent side to the hypotenuse. So what is the adjacent side with respect to angle C? 10 centimeters is counted as the hypotenuse. So the adjacent side with respect to angle C is 8 centimeters. So adjacent side is 8 centimeters and the hypotenuse is 10 centimeters. So again centimeter cancels. So this is 8 upon 10. 8 upon 10 can be simplified as 4 upon 5. Do you notice that the ratio of the adjacent side to the hypotenuse also remains 4 upon 5, right? So this is the other conclusion that I can come to. Let's note the conclusion. So as long as the angle remains constant or the same, the ratio of adjacent side to the hypotenuse also remains the same. So the ratio of adjacent to hypotenuse is 4/5 and the ratio of adjacent to hypotenuse here is also 4/5. So what we are trying to say is, as long as you keep angles constant, the ratio of the sides of a triangle remains constant. These ratios are called trigonometric ratios. Okay. So trigonometric ratios are basically nothing but the ratios of the different sides of a given triangle. Right now you will always have a right angle triangle for study, but these ratios are applicable for all angles. Again, because these are ratios of different sides, these ratios have no units, right? There is no unit to these ratios, and we will now study more about these trigonometric ratios. These trigonometric ratios are also known as T ratios. Okay, so now I am going to pause for a minute. I am going to let you take a look at all these calculations that we did here, and after a minute we will study this particular topic in greater detail. So let us now understand these trigonometric ratios in greater depth. Consider I have a right angle triangle ABC and assume that angle C is the angle of reference right now, right? With respect to angle C, so let's note down a few things here. With respect to angle C, AB forms my opposite side. AB is the opposite side. Then BC forms the adjacent side. So BC is the adjacent side. And AC is the hypotenuse. AC is the hypotenuse. Let me quickly draw arrows to illustrate this. With respect to angle C, AB is the opposite side. BC is the adjacent side. And AC is the hypotenuse. Let us now study the same things with respect to angle A. So with respect to angle A, I have drawn a different triangle here. With respect to angle A, the opposite side, so let's draw the arrows. The opposite side is BC. So let's note that down. BC is the opposite side. then AB is the adjacent side. AB is the adjacent side. And AC forms my hypotenuse. AC forms my hypotenuse. Right? So the hypotenuse, you notice, remains the same throughout, but the definition of opposite and adjacent sides changes with respect to the angle. So this brings us to an important conclusion, that the trigonometric ratios that we are going to study, the trigonometric ratios are heavily dependent upon the angle, right? The definition of the opposite and adjacent changes with respect to the angle, and that is why the trigonometric ratios are going to depend on which angle is under consideration. So let us take some examples now. Let us now write all the possible ratios that you can have in a given triangle. Let us assume that P is the angle that is under consideration right now. With respect to angle P, QR is the opposite side. So let us mark it. QR is the opposite side. PQ is the adjacent side. And PR is the hypotenuse. Now what ratios are possible? One ratio is opposite upon hypotenuse. The other ratio is adjacent upon hypotenuse. Adjacent upon hypotenuse. And the third ratio that I can find is opposite upon adjacent. Right? Similarly, the reciprocal of all these ratios is also possible. The reciprocal of opposite by hypotenuse will be hypotenuse upon opposite. The reciprocal of adjacent upon hypotenuse is going to be hypotenuse upon adjacent. And the ratio of opposite to adjacent is going to be adjacent upon opposite, right? So these are the 6 ratios that are possible. And now let us assign some specific names to these ratios. The ratio opposite upon hypotenuse is called sine of that angle. So sine P is the ratio of the opposite side to the hypotenuse. The short form of sine can also be written as sin P, but please remember this is not sin, it is sine. So sine of an angle is the ratio of the opposite side to the hypotenuse. The ratio of adjacent to hypotenuse is labeled as cosine, and the short form of cosine is cos. So cos of P is basically going to be the ratio of adjacent side to the hypotenuse side. The ratio opposite to adjacent is written as tangent of theta, or tangent of that angle. So cosine P will be adjacent by opposite. Tangent P will be opposite by adjacent, but tangent, the short form of it is tan P. To make this simpler, there are some shortcuts. Sine is opposite upon hypotenuse, so the short form for it is SOH. S-O-H. S stands for sine, O stands for opposite, and H stands for hypotenuse. The short form for cosine is therefore CAH, C-A-H, where C represents cosine, A represents adjacent, and H represents hypotenuse. Similarly, the short form for tan is TOA, where T stands for tan, O stands for opposite, and A stands for adjacent. So now we have learned 3 ratios. The first one was sine, which was opposite upon hypotenuse. Then we have learned cosine, which was adjacent upon hypotenuse. And then we learned tan of an angle, which is opposite upon adjacent. So we have saw, we have ka, and we have toa. The reciprocal of these ratios are, so the reciprocal of sine is opposite upon hypotenuse. The reciprocal of this is called cosecant of an angle. So cosecant of P, or the short form of this is just cosec of that angle, right? So cosec is the reciprocal of sine. The reciprocal of cos is adjacent upon hypotenuse. The reciprocal of adjacent upon hypotenuse is hypotenuse upon adjacent, which is known as secant of an angle. Of course, its short form is simply sec of the angle, so sec P. And adjacent upon opposite, which is the reciprocal of tan. So if you notice, tan of an angle was opposite upon adjacent. The reciprocal of this ratio is called cotangent of the angle, that is cotangent of P. The short form of this is cot P, right? So we have 6 trigonometric ratios over here. I will pause for a minute before I take an example in this diagram. So let me explain this better with an example. Consider that you have triangle ABC. Let AB be 9 centimeters and let BC be 12 centimeters. Using Pythagoras theorem, you can definitely find AC. So I will say, using Pythagoras theorem, we have AC square is equal to AB square plus BC square. AC square is equal to 9 square plus 12 square. 9 square is 81 and 12 square is 144, which is equal to 225. So AC square is 225 means AC is square root of 225, which is basically 15 centimeters. So the hypotenuse that you have here is 15 centimeters. Now what I am going to do is, I am going to find the trigonometric ratios of angle A first. Okay. So let us quickly find the trigonometric ratios of angle A. The 6 trigonometric ratios, if you remember, were sine. So sine A, then we have cos A, then we have tan A, right? And their reciprocals. So let us first find these 3 ratios and then we will find their reciprocals. Sine, if you remember the short form for sine, sine was opposite upon hypotenuse. With respect to angle A, the opposite side is 12 centimeters. With respect to angle A, the adjacent side is 9 centimeters and the hypotenuse happens to be 15 centimeters. So sine is opposite upon hypotenuse. Opposite is BC divided by the hypotenuse is AC. BC is 12 centimeters and AC is 15 centimeters. So 12 divided by 15 is 4 by 5. So sine A is basically 4 by 5. cos A. Let's remember the short form for cos of an angle. Cos was ka, that is adjacent upon hypotenuse. So which is the adjacent side of angle A? Adjacent side is AB divided by hypotenuse is AC. AB is 9 centimeters divided by the hypotenuse is 15 centimeters. The ratio of 9 to 15 is 3/5. Similarly, let's find tan A. The short form for tan is TOA, which is tan is opposite upon adjacent. With respect to angle A, the opposite side is BC and the adjacent side is AB. So this is given by 12 centimeters by 9 centimeters, which is going to be 4/3, right? So tan A is therefore 4/3. Now finding the reciprocals is going to be very easy. Sine A is 4/5. Reciprocal of sine is cosec A. So cosec A is going to be 5/4. Cos A is 3/5. Reciprocal of cos is sec. So sec A is going to be 5/3. I am simply finding the reciprocal of the ratio. Tan A is 4/3. The reciprocal of tan is cot. So cot A is given by 3/4. These are the 6 trigonometric ratios for angle A. I am going to pause for a minute and then I am going to go ahead and find the trigonometric ratios for angle C. Okay, so let me pause for a minute so that you can take a look at the calculations on the board, and then we will find the trigonometric ratios of angle C. So now let us go ahead and find the trigonometric ratios for angle C in the same triangle. So you will notice that because the angle has changed, the references of opposite and adjacent side will also change. So now consider angle C as the reference. So if angle C is the reference, the definition of opposite side and adjacent side will be as follows. With respect to angle C, the opposite side is 9 centimeters and the adjacent side is 12 centimeters, whereas 15 centimeters is the hypotenuse. So again there are 6 trigonometric ratios. One is sin C, one is cos C, one is tan C. So let us find the trigonometric value of sin C. Sin is opposite, which is 9 centimeter, divided by the hypotenuse, which is 15 centimeters. So this is 9/15, which is 3/5. Cos C, cos is adjacent, that is 12 centimeters, divided by the hypotenuse, which is 15 centimeters. That's going to be 4/5. And tan C, tan is the opposite side, which is 9 centimeters, divided by the adjacent side, which is 12 centimeters. So tan is 3/4. If you take the reciprocal of these ratios, the reciprocal of sin is cosec C. So cosec C is therefore 5 upon 3. Sec C is 5 upon 4. And tan C, the reciprocal of tan C is cot C. Cot C is 4 upon 3. So these are the 6 trigonometric ratios of angle C. So it is as simple as this. When you notice a triangle given to you, you try to find, first you should understand which is your angle of reference. If you notice trigonometric ratios exist for a certain angle. So in the first case, angle A was the reference. In the second case, angle C was the reference. Based on that angle, you find out the opposite, adjacent and the hypotenuse within that right angle triangle. And once you get those opposite, adjacent and hypotenuses, you can then find the trigonometric ratios. So I will again pause for a minute and then I will show you some problems based on trigonometry. So let's consider the following questions for trigonometry. So consider this right angle triangle where the measurements are given. Angle B is the right angled vertex. So let's color it. We know that the hypotenuse is 13 and one of its sides is 5. So using Pythagoras theorem, you can definitely find the side BC. So let's say using Pythagoras theorem in triangle ABC, we get AC square is equal to AB square plus BC square. AC square is 13 square, which is equal to 5 square plus BC square. So 169 is equal to 25 plus BC square. So 169 minus 25 is 144. 144 is equal to BC square, which means BC is 12 units, right? So the length BC is therefore 12 units. Now we have to find sine A. So what is the value of sine A? Here A is the angle of reference. So let us mark it. Sine is given by, if you remember the short form for sine was SOH, that is SOH, which is sine is opposite upon hypotenuse. So with respect to angle A, which is the opposite? Opposite is 12 units. Divided by hypotenuse, hypotenuse is 13 units. And therefore sine A is given by 12 upon 13. So if I want to find cos C, let us now find cos C. So now which is the angle of reference? It is not A anymore. We are finding cos C, which means angle C is the angle of reference. So with respect to angle C, what is the definition of cos? Cos is given by adjacent upon hypotenuse. With respect to angle C, 12 units is the adjacent. So it is 12 units divided by the hypotenuse is 13 units. Again, remember that cos was ka, that is adjacent upon hypotenuse. So this ratio is 12 upon 13. Then I want to find tan A. So again, now the angle of reference has changed. So let us quickly mark the new angle of reference. So now angle A is the angle of reference. Let's mark it. So angle A is the angle of reference. Tan is given by opposite, that's 12 units. divided by the adjacent. The adjacent is 5 units. And therefore tan A is given by 12 upon 5. Then we have cosec C. So if you remember, cosec is the reciprocal of sine. So let me first find sine C. So now angle C is the angle of reference, which means that this is the angle of reference. Sine is given by, the short form for sine is SO. Sine is opposite, which is 5 units, divided by the hypotenuse, which is 13 units, and therefore sine is 5 upon 13. This means cosec. Cosec is the reciprocal of sine. Cosec is therefore going to be 13 upon 5. Right? So this is how I can find the value of cosec of an angle. Now I need to find sec square A minus tan square A. So we need to find sec A and tan A first. Okay, let me pause for a minute, take a look at what all was done, and then we will solve the fifth subpart. So now let's find the fifth subpart. Fifth subpart is sec square A minus tan square A. Sec A is the reciprocal of cos. So let us find sec A first. So for that, now angle A is my angle of reference. So let's find cos A first. Cos A is given by the adjacent side, which is 5, divided by the hypotenuse, which is 13. And therefore sec A will be the reciprocal of cos. So sec A will be 1 by cos, which is 13 upon 5. So we found sec A first. Now do we have the value of tan A? I think yes, we have the value of tan A. Tan A is 12 upon 5. So now we need to find sec square A minus tan square A. That is going to be 13 upon 5 the whole square. 13 upon 5 the whole square minus 12 upon 5 the whole square. That is 169 minus 144 divided by 25, which is going to be 25 by 25, and that is going to be equal to 1. So this is how I solved this particular problem. Pausing for a few seconds before moving on to my next question. Let us solve one more question based on trigonometry. So let's take a look at this particular question. Triangle ABC is right angled at B. We have to find the trigonometric ratios of angles A and C. So first let us find all the trigonometric ratios of angle A. So let us mark angle A first. So now I can first use Pythagoras Theorem to find the length of AC. So I will say using Pythagoras Theorem, I get AC square is equal to AB square plus BC square, which is 8 square plus 15 square. 8 square is 64, 15 square is 225, that equals 289. So AC square is equal to 289, which means AC square root of 289. Square root of 289 is 17 centimeters. So the length of the hypotenuse is therefore 17 centimeters. Now let's go ahead and find the trigonometric ratios of all angles. So of angles A and C. So let us first pick angle A as our angle of reference. So this is angle A. So I have 6 trigonometric ratios. So let's say sine A, then let's have cos A, let's have tan A. So sine is the opposite side. So with respect to A, angle A, 15 is the opposite side and 8 centimeter is the adjacent side, while 17 remains the hypotenuse. So sine, if you remember, is saw, that's opposite, which is 15 centimeters divided by the hypotenuse, which is 17 centimeters. The answer is therefore 15 upon 70. Cosine is ka. So cosine is adjacent, which is 8 centimeters divided by 17 centimeters, which is 8 upon 17. And tan is 2a. So tan is opposite, that's 15 centimeter divided by adjacent, which is 8 centimeter. Therefore, this is 15 upon 8. And now we can find the reciprocals of these ratios. Sine's reciprocal is cosec. So cosec A will be 17 upon 15. The reciprocal of cos is sec. So sec A is 17 upon 8. And the reciprocal of tan is cot A. So cot A will be 8 upon 15, right? These are the trigonometric ratios of angle A. Similarly, we can now go ahead and find the trigonometric ratios of angle C. So now please note that the angle of reference has changed, and therefore the definition of adjacent and opposite sides will also change. So angle C is the angle of reference now. So angle C is the angle of reference. So let us mark that particular angle. With respect to angle C, 8 centimeter will be the opposite side and 15 centimeter will be the adjacent side. Therefore, sin C, cos C, tan C. Sin C will be the opposite side, which is 8 centimeter upon hypotenuse, which is 17 centimeter, that is 8 upon 17. Cos C is the adjacent side is 15 centimeter divided by hypotenuse, which is 17 centimeter, that is 15 upon 17. And tan C is the opposite side, which is 8 centimeter divided by the adjacent, which is 15 centimeter, which is 8 upon 15. So these are the 3 trigonometric ratios of angle C. Now we can find the reciprocals. Sine's reciprocal is cosec. So cosec C will therefore be 17 upon 8. Then we have the reciprocal of cos is sec. So sec of C will be the reciprocal, which is 17 upon 50. And cot of C, cot C is the reciprocal of tan, which is going to be 15 upon 8. So this is how we find the trigonometric ratios of the given angles. And I conclude the session over here today with this problem. I will pause for a minute before shutting down the video. concluding today's session here.